anybody's ever accessed, but the recordings are all on Blackboard in the class recording section. So you can refer to go back to any class, gives you, there's a caption that tells you exactly what topic is being covered in each lesson, in addition to the date that it was given. Okay, let's start going over number one. This was not, I didn't give this as a multiple choice, but remember your final exam, which is on Thursday, December 15th, don't forget, is going to be a multiple choice test. As far as I know, there's been no change since the proper class terms. It's going to be 30 multiple choice questions on Blackboard the same way that the midterm was. It'll be in its own section. You'll open up, once it's posted, you'll open up your Blackboard account and it'll have a section that will say final, and that's where you're going to go. Don't forget also, you should be doing the practice final. And if you didn't like the mark you got a first time, you can do it second time, even a third time. You do it a few times and your best mark will be counted as a class test mark. I will give you an indication as to how I'm going to figure out your grades. I'll do that probably on Friday. Okay, looking at question number one, where we have one fraction divided by another. What we know is that we have to change it to a multiplication problem by taking the reciprocal of the second fraction. Also, we know that we have to factor everything so that we can see if we can reduce or cross reduce or cancel anything out. So I'm going to do those two things together. I'm going to factor everything, and as I rewrite it, I'm going to rewrite the second fraction as a reciprocal. So looking at the 36x squared minus 1, if we want to factor that, we see it's what we call the difference of squares. It's 6x plus 1 times 6x minus 1. Remember, when you're factoring binomials, look if your first term is a perfect square and your second term, so that you can divide it into two binomials. The denominator, x squared minus 25, is also the difference of squares, so I can break that up into x plus 5 and x minus 5. Remember, you get the two binomials looking identical, except one is plus and one is minus. In other words, conjugate binomials. Now I'm going to change this division to a multiplication by putting the x plus 5 on the top and the 6x plus 1 on the bottom. And now I see that this 6x plus 1 can cancel out with this 6x plus 1, which will leave me just a 1 over here. Remember, if everything disappears, then you're left with a 1. It's not a 0, it's a 1. The x plus 5 on the top cancels out with the x plus 5. You can't cancel out an x plus 5 with an x minus 5. Just an x plus 5 with an x plus 5. So that your final answer comes out to be 6x minus 1 on the top and x minus 5 on the bottom. That would be your answer in simplest form. And again, these examples that I'm giving you came off of finals, so therefore you know this is the type of thing you have to know how to do. Looking at question number 2, this is what is a rational or fractional equation. It's an equation with fractions in it. And what we said, the first thing we're going to do is find what we call the LCD, the lowest common denominator. And we do that by factoring all the denominators. Well, the x plus 5 and the x can't be factored any further. but the x squared minus plus 5x can be factored to x plus 5. There is a common factor of x. Now, if you recall how we figure out the LCD, we start with our first fraction and we take all the terms, all the factors from that denominator, which is x plus 5. Then we go to our next fraction. And if it's x plus 5, then I don't have to write it again. But this is a different factor. This is x. I'm going to put it in front, though it doesn't have to be, it doesn't matter whether it's in front or in back. And then I go over here, and I already have the x, and I already have the x plus 5. So our LCD turns out to be the x plus 5 times the x. Now what we do is we take that least common denominator, the x times the x plus 5, we put it over 1, and we multiply the whole equation by it, which means I'm going to have to multiply each term in the equation by this common denominator. I'm distributing it. So I'm going to multiply x times x plus 5 over 1 times 6 over x plus 5 plus x times x plus 5 over 1 times 7 over x equals x times x plus 5 over 1 times 2x plus 5 over x times x plus 5. In other words, we take the common denominator, put it over 1, and multiply it. As long as I'm multiplying everything by it, I'm not changing my fraction. I can multiply. You have to do it on both sides of the equation. So let's see what happens over here. In this first fraction, the x plus 5 cancels out with the x plus 5. And I'm left with an x times a 6, which is just 6x. In the second fraction, I have an x that I'm canceling out with an x. And I'm left with the 7 and the x plus 5. These are the two things I'm left with. Notice my denominators all disappear.
That's not even funny. Like, I'm not doing it at all. Because there's no reason why I'm sitting on a train, you know, trying to make it to work. And if I want to be doing that,
Sanaya, we can hear you. And that equals, so that's why I don't have to put anything in the bottom, because my bottoms are all turning out to be 1. I made that happen by picking the common denominator. Now on the other side, the x cancels with the x, and the x plus 5 cancels with the x plus 5. So all I'm left with is 2x plus 5. In other words, once I've multiplied my whole equation through by the least common denominator, I'm left with a very simple equation to solve. I have to remove this parentheses, so I'll be left with 6x plus 7x plus 35. Don't forget I'm distributing the 7 equals 2x plus 5. 6x plus 7x gives me 13x plus 35 equals 2x plus 5. I'm going to minus 2x from both sides. And I'm going to minus 35 from both sides, so that I'm left with only numbers, only variables on the left side and only numbers on the right side. So 13x minus 2x gives me 11x. The 35 cancels out, the 2x's cancel out, and here I got 5 minus 35, which is negative 30. And I divide both sides by 11, And my answer is negative 30/11, which is choice D. I think that is the choice that you picked. Let me see. Yes, Tahira, you are completely correct. Okay. Let's now try a couple more problems from this chapter. Okay, so we talked about multiplying fractions and dividing fractions. Remember, the difference between multiplying and dividing is simply at your start. If it's a division example, you flip over your second fraction. You take the reciprocal of your second fraction and then you just multiply. When you're solving an equation, you try to find the common denominator. Okay, let me put on another problem for you to try that is from this chapter. I'm going to erase this. Can I erase the rest of it? Okay. What if I gave you this problem? Give you x over x plus 6 minus 72 over x squared minus 36. And I want this in simplest form. I want you to combine the two fractions. Actually, this is a subtraction of two fractions. I want you to combine them and get your answer as simple as possible. Okay, I'm going to give you a few minutes to try that. While you're doing that, I will take attendance. We'll look at the participants. Okay. Okay, so MIC, you're here. Naya, you're here. Isis, you're here.
Good morning.
Good morning. Jean, you're here. Kayla, you're here. Always nice and early, Kayla. Thank you. Ariana. Sanjita.
Yes, Professor.
Hi. Good morning.
Good morning.
Shania. Shakira. Okay. I see Jean has sent us an answer. Let me give you some. Okay, I'm giving you one more minute to try this. And then we'll see if Jean came up with the right answer. Okay, so let's try this. Just like when you're solving rational equations, when you're trying to combine, that means add or subtract fractions or rational equations, you need to find the least common denominator. When you're multiplying and dividing, you don't have to. But for adding, subtracting, and solving equations, you have to find the LCD. And in order to do that, what we've got to do is factor our denominators. Well, the x plus 6 can't be factored anymore, but the x squared minus 36 is that famous factoring of difference of squares. It's x plus 6 and x minus 6. And remember how you write your LCD. You start at your first fraction and take all the factors in that first fraction, which is just x plus 6. You then go to your next fraction and you check. I already wrote down the x plus 6. I don't have to write it again, but I don't have the x minus 6, so now I have to put in the x minus 6. And I'm going to, I'm not going to multiply by the common denominator. I'm going to make sure that each of the fractions have a common denominator of x plus 6 and x minus 6. So that's the difference between solving an equation and adding and subtracting the fractions. In solving an equation, you take the common denominator, put it over 1, and distribute it. But you can't do that over here. You're just going to end up with both of these factors in your denominator. Okay, once we found out what our common denominator is, we then have to rename the fractions with that common denominator. So I compare, that's why I try to put it one right underneath the other. I take the original first fraction, I see that the original denominator was x plus 6. So I want my new denominator to be x plus 6 times x minus 6. So I have to take the x that's on top and multiply it by the x minus 6. I multiply the bottom by x minus 6. I've got to multiply the top by x minus 6 as well. Okay, and I'm going to have to simplify it, but I'm just figuring out what to do. In my second fraction, I have the x plus 6 and the x minus 6. I haven't changed my denominator from the original, so I don't have to do anything with the numerator. So I leave it 72. What does that give me? That gives me x squared minus 6x minus 72. Because I'm combining all of these now. Don't forget that this is a minus, so it's subtracting everything, but it's only one term. And put it over the common denominator, x plus 6 and x minus 6. Now I've combined everything. Now I want to simplify because it said I wanted it in the simplest form. So I'm going to try and factor the numerator. The denominator is already factored to x plus 6 and x minus 6. Well, this is an easier type factoring of a trinomial because it's starting with a leading coefficient of 1. It's just starting with an x squared. So I break it up into x and x. Since the last term is negative, 1 is going to be positive, 1 is going to be negative. And I need two numbers that multiply to 72 and subtract to 6. Now, you might realize the numbers right away, but you could always do this. 2 times 36 is 72. Well, that doesn't subtract to 6. 3, remember, just keep dividing it. 3 times 24 is 72. But that's also not a difference of 6. 4 times 18. And I'm doing this, I could do this just with my calculator. Just keep dividing it by numbers. 4 minus 18 minus 4 is not 6. Keep going. 5 doesn't work because 5 doesn't go into 30. Excuse me. Hello? So we don't even, 5 doesn't go into 72, so we can skip that. 6 times 12, I divide 72 by 6, I get 12. That 6 times 12 is 72. And when I subtract 12 by 6, I get 6. So I hit the right combination. So you could just do it. If you can't, don't see it immediately, just take your calculator and work with your calculator and take the big number and divide it by 2, divide it by 3, by 4. Eventually you're coming out with the right combination. Okay, so I know my two numbers are going to be 6 and 12, but since the middle term is negative, I know I have to put the 12 with the negative and the 6 with the positive. And now I see the x plus 6 with the x plus 6 cancels out. So my final answer is x minus 12 over x minus 6. And I think that is the answer that you gave me. Perfect, Jean. Thank you. Okay. So now let's do one more problem from this chapter. And I'd say, unless somebody has a particular problem they'd like me to do, I'd say we're in pretty good shape. Again, if you're doing the practice final and you're coming across a problem that you're really having a trouble with, you can certainly bring it up in class and we'll do it together. Okay, so here's our next question. Suppose I want you to divide 3x to the third minus x squared plus 2x plus 6. That's a 4-term polynomial by the polynomial x plus 1. If you remember, this is what we call long division. We have to set it up with the x plus 1. I'm just going to start it and then I'm going to give you time to work on it. The x plus 1 will go on the outside. That's what's called the divisor. The polynomial is called the dividend. That's what we're dividing into. When we have to make sure it's in descending order, which means the highest power term first, which is x to the third, that's good. After the x to the third, there has to be an x squared term, which we have. Remember, if a term is missing, if there would have been no x squared term, we would have had to put negative minus 0 or minus or plus 0x squared. You have to account for every term. After the x squared, there has to be an x term. Well, there is one, so it's 2x. And after that, there has to be a plain number, and there is. There was nothing missing, and it was in descending order. Okay, I'm going to give you a few minutes to try and do this long division. See if you remember how to do that. Okay, let's work on this together. We've got it set up properly. If you recall what we do when we're doing this long division, which we do when we have a polynomial divided by a binomial or by any polynomial, but basically by a binomial, we have to set it up as this long division. And when we start the division, we take our first term. We don't look at the plus one, we just look at the x, and we divide it into the first term. So we're always going to divide, when we're doing the division, we're always going to be taking the first term into the first term. So this is a 1x, so the 1 goes into the 3 times, and the x goes into the x to the third. Remember, when you're dividing, you're subtracting exponents. This is an exponent of 3. This is understood to be an exponent of 1. 3 minus 1 is 2. So this is going to give us 3x squared. Now, you do not have to be careful as to where on top you put it. This is not like number long division, where if you don't put it in the right place, it's not going to work out. It doesn't matter where you put it on top, as long as you put it on top. After you take what's on top, you take that and multiply it by the whole binomial. So you're going to do the 3x squared times the x, which will give you 3x to the third. And then you're going to take the 3x squared and multiply it by the plus 1. So that's going to give you plus 3x squared. So even though when you divide it, you only use the first term, when you multiply, you actually multiply by the whole binomial. After you've done that, the next thing you have to do is subtract. And you'll see that things have been lined up because if we did the setup right, everything's going to line up. And don't forget, when you're subtracting, you're going to be changing the signs. Now, this is a positive 3x cubed, so it's going to become a negative. And this positive is also going to become a negative. So we'll end up with 3x cubed minus 3x squared that cubed that cancels out. And now I have a negative x squared and a negative 3x squared. Don't forget that x squared became negative because we're subtracting it. And a negative, that gives us negative 4x squared. Be very careful with your signs. After you've done that, you bring your next term down, which is plus 2x. And you start the process all over again. I am sorry about that. Okay, I'm going to take now the x and divide it into the negative 4x squared. Again, I'm going to divide the first term into the first term. So 1 into negative 4 gives me negative 4, and x into x squared gives me x. Now, take what you just put on top, the negative 4x, and multiply it by your binomial. Negative 4x times x is negative 4x. Where? Negative 4x times 1 is negative 4x. And again, we're now going to subtract. So we're going to change the signs. This is going to become a plus. And I'll get negative 4x squared minus plus 4x squared. That cancels out. And this is also going to become a plus. So this is going to be 2x plus 4x, which will give us 6x. And now again, I do the same thing. I bring down the next term, the plus 6. And I divide the first term into the first term. So 1x into 6x, the 1 into 6 goes 6. And the x into the x cancels out. So I'm just left with a plain 6, not 6x, it's just 6. I'm going to take the 6 that I just put on top and multiply. 6 times x is 6x. 6 times 1 is 6. And now I'm going to subtract. So this is going to become a minus, and this is going to become a minus. and they both cancels out. So my final answer, there's no remainder, is 3x squared minus 4x plus 6. Don't forget that's what we call long division when you're asked to give the answer of dividing a polynomial by a polynomial, where it'll ask you to divide and give the quotient, which is the answer, 3x squared minus 4x plus 6. And the remainder, sometimes we take the remainder, there was no remainder in this case, but if let's say the remainder would have been 7, I would have put plus 7 over x plus 1. I take the remainder and put it over the divisor. So that's how we divide polynomials. Okay. So having said that, I'd like to now go back to the study of logs and go a little bit further. Each day we're going to, I hope to be finished by the topic by Friday. Again, we have 3 more sessions after today, Friday, Monday, and Wednesday. And next Thursday is our final exam. This is just a week. So now's the crunch time. You should be spending time. Now, if you were here on Friday or the day before, we talked about exponential equations and things that are in exponential form, something like b to the c equals a. We can say the exact same thing in what we call logarithmic form. It's telling us the same exact information, it's just in a different format, where we write the word log. The base is the subscript. The number on the other side of the equal side, what the log is equal to, is the exponent, because the word log really means exponent. And the number that you get, the a, goes right next to the word log. That if you read this, this is the correct way to read this is log base b of a equals c. And again, if instead of the word log, you write the word exponent, it'll make a lot of sense. The exponent of base b that gives you a is c. In other words, the log is the exponent. The log means exponent. And that's exactly what it's telling us. If you take your base, which is always a subscript, and put it to the exponent, which in that case is c, you're going to get a. So if I were to give you a question like this, where I'd say find the value of log base 2 of 8. Say I ask you, that's your question. Most of the time when you have a question about logs, it's easier to solve if you take it and put it in the exponential form. Now, if you notice in both of these, in the log form, the exponential form, there always are 3 numbers. There's the base, the exponent, and what it equals to. If one of those numbers are missing, which in this case they are, well, it's not equal to anything, let's put it equal to x. We don't have, they didn't tell us equal to x, obviously we know it's equal to x. And therefore we can now switch it. Since we have it in logarithmic form, we can switch it to exponential form by taking the base 2, that's always the subscript. The exponent is a number on the other side, so that's the x, is going to be equal to a. This is saying exactly the same thing as this. Again, if you can, the important thing is to be able to switch from log form to exponential and vice versa, because then it makes it, we're much more aware of things in exponential form than we are in log form. Now let's think if we can do this. 2 to what exponent is going to give us 8? Well, let's just do it. 2 times 2 is 4, times 2 is 8. How many times am I multiplying the 2? Obviously 3 times. So obviously the exponent would have to be 3. So our answer in this case would be x, or this is equal to 3. Okay. How about, I'm going to give you one to try. Just change this change to exponential form. Log base 5 of 1/25 equals -2. This is in logarithmic form. I'm giving you a minute to change it to exponential form. Okay, I think most people should have been able to do this. Again, there's no figuring out here. We just have to switch it from one format to the other. So we're going to first, remember how we do. We first look for our base. Our base is a subscript. So that has to be 5. The exponent has to be the number on the other side of the equal sign. The log equals, the exponent equals. So my exponent is -2, and that has to equal 1/25. Now, they didn't ask us to figure anything out. They just asked us to change from logarithmic form to exponential form. Sometimes that's all they ask you to do. Notice it makes sense because if you remember, a negative exponent means that you're going to have a fraction. This is 1/5 squared, or 1/25. So it makes sense, but they weren't even asking you, does it make sense or not? Just switch it. Okay, so having these two things and remembering this, let's go a step further in our study of logs, or logarithms, if you want to call it logarithms. What we're going to be talking about today are the properties of logarithms. How do we combine logarithms? How does working with logarithms compare with working with regular numbers? And the rules I'm going to tell you will make sense if you keep in mind that logs are really exponents. So here they're basically 3 rules. I'm going to talk about the first 2, and then we'll talk about the third. The first rule is, and I'm writing it the way I wrote it on the study guide, so it'll make more sense to you. If you have the log base b of 2 numbers, x times y, x are just any old numbers. X and y are any 2 numbers. I don't know what they are, so I've been calling them x and y. And we take the log. What's going to happen? Usually you think, oh, I should just take the log of x and multiply it by the log of y. But it doesn't work that way. Why? Because these are not algebraic functions. These are what we call transcendental functions. They don't work like regular algebra. So we have to think, what would have happened if I were multiplying two numbers? What would happen to their exponents? Because that's what the logs are. And obviously, we know when we're multiplying two numbers, as long as the base is the same, and this case, we are using the same base because we're using a base B. I don't know what it is, but it's the same base. Whenever we multiply two numbers with the same base, what we do is we add their exponents. So the first rule that we're going to have is that when we're multiplying two numbers, what we're going to do to their exponents or their logs is add them. That's rule number one. What's rule number two? If I have the log base B of X divided by Y. Well, what's the rule when we're dividing numbers? What do we do to their exponents? We know what we do. We subtract the exponents. So this rule is going to be the log base B of X minus the log base B of Y. Remember, the word log means exponent. If you have something that's a fraction and it's raised to an exponent, what you do to the two, you subtract the exponents. Remember, the logs are the exponents. So what do we do to the exponents when we're dividing? We subtract the exponents. So that's why we subtract the logs. Okay, the third rule has to do with exponents. Let's say I have the log base B of X to the nth power. I have something to an exponent. Now remember, the log is one exponent, and I'm raising it to another exponent. In other words, I have some number, let's say it's B to the 7th. I think maybe that's B to the 7th is my X. And I'm raising it to another exponent. Let's say we're raising it to the exponent 2. So what do we do to the two exponents? Well, we know we multiply the two exponents. Now remember, the log is just the exponents. So what have I done with this exponent 2 with the log, which was the 7? We multiplied them. So in order to give us a rule, the easiest way to write this rule is to take, remember, the log is one exponent, we're raising it to another exponent, take the new exponent, the n, and multiply it by the original exponent, which is a log base B of X. In other words, your exponent is going to become your coefficient. Now, there is a sub-rule to this. For example, what if I asked you for the log base B of the cube root, let's say, of X? I didn't tell you anything about radicals, except last week we talked about it, that there's an alternate way to write a radical. We could write this as X to the 1/3. Any radical can be written as an exponent where it's a fractional exponent and the denominator of the fraction happens to be what the index is. Remember, if it's just a plain square root, the index is 2. So if this would have been plain X, the square root of X, this would have been X to the 1/2. But then I can use this rule. I have the log base B of X to the 1/3 power. Remember what I said, what happens with your exponent? It becomes your coefficient. So this becomes 1/3 log base B of X. So there are these three rules. Again, this radical rule is just a part of rule 3 that I call the rules of logarithmetic. And we have to remember, when we're working with logs, what we're actually doing is working with exponents, and the properties and the rules that apply to logs are the rules that apply to exponents. Now, the question is, what kind of questions could you get that involve these problems that have to do with properties of law? So let me give you a couple of examples. Okay, one of the things that we're asked to do, and I'm going to erase this, but you have to have these rules. These 3 rules you have to know. I just don't have room on my board. I can't keep the rules on the board and do problems. So I'm now going to erase this. I hope everybody has these rules written down. And one of the questions that are sometimes asked has to do with, it says, use the properties of log to expand the expression. So what does that mean? Well, let's take something like this. Suppose I'm given log base, I'm giving us log base 6 of x squared y4. And what do they mean by expand? They want me to write this in terms of just a log of a single number. Now, there are actually 2 numbers or 2 letters. There's an x and a y. So I have to have something with a log of x and something with a log of y. So remember, I'm going to use the properties that I just talked about. The first thing I'm going to always look for when I want to expand something into individual logs, I'm going to look if there's any multiplication or division involved in the expression. And of course, there's no division, but there is a multiplication. And we're multiplying x squared times y4. But when we're multiplying the numbers, what do we do to the exponents? We add them. So we're going to rewrite this as log base 6 of x squared plus log base 6 of y to the 4th. Now I have to write the word log in front of each expression because the log is telling me that we're talking about the exponents. So I can't just do x squared plus y 4th because that would be wrong. I'm multiplying x squared times y 4th, but what I'm doing to their logs, to their exponents, is I'm adding them. There's one more thing I can do to simplify, and that's look if there are any exponents, because if you recall, I said when you have an exponent, the exponent is really something that we're multiplying by when we're dealing with exponents. If we have 2 exponents on the same number, we multiply those 2 exponents. So the new exponent becomes the coefficient. So this becomes 2 log base 6 of x. And the 4 here again goes in front, plus 4 log base 6 of y. Notice the fact that it's log base 6 doesn't make a difference. It could be any base. What we're going to do is we're going to take the log of x multiplied by 2 and add it to the log of y multiplied by 4. And now we're saying exactly, this is why it's called expanded, because it's telling you what to do to each individual log. Again, Keep in mind, logs mean exponents. Let's do another one. I'm gonna do one or two more, and then I'm gonna give you some to try on your own. Suppose I gave you this expression, log base 7 of the cube root of x over z squared y. And again, I want to expand this expression. Into individual logs. Well, anytime I'm working with the logs or exponentials and I come across a radical, I know I have to rewrite that radical as an exponent. So I'm going to rewrite this as log base 7. Instead of the cube root of x, I'm going to write that as x to the 1/3 power. Any radical can be changed to an exponent. It's a fractional exponent. And that's over z squared y. Okay. Now I have my thing set up so I can start working with it. I have everything written in terms of letters and exponents. Now, remember what I told you to do. First, deal with the multiplication and division, and then we'll go back and deal with the exponents. So we have two things happening here. I have two numbers being multiplied, but they're both being divided. The x 1/3 is being divided by both of them. So when I expand that, it's going to be the log base 7 of x to the 1/3 minus, now I'm going to have to put this in parentheses because I'm subtracting this whole thing because this whole thing is in the denominator. This is going to be the log base 7 of z squared plus the log base 7 of y. And I'm going to remove the parentheses, so it'll give me log base 7 x to the 1/3 minus log base 7 z squared minus log base 7 of y. Notice both the logs of the z squared and the y are negative. And you can keep this in mind. This is where most people would make a mistake. They would subtract the log of the z squared, but add the log of the y. But the y is also being divided by because it's in the denominator. I'm not quite finished yet because I have a couple of numbers that have exponents. And remember, I just take the exponents, in this case it's 1/3, and put it as a coefficient. So it's 1/3 log x minus 2 log base 7 z minus log base 7 y. Just keep whatever base, it doesn't matter what the base is, but just keep it the same throughout. You can't switch bases in the middle. And this would be your expression in its expanded form. Let's see if you can do this one. See if you can expand this. Log base 6 of x fourth y to the third over z squared. Expanded like we did this one. Give you a couple of minutes to try that. Okay, let's see if we can do this together. I'm going to erase this so I can do the problem. So we have log base 6 of x to the fourth, y to the third, divided by z to the second power. Okay, and we want to expand this. So we first look for multiplications and divisions. And I see the two top numbers are multiplied, so I'm going to do log base 6 of x to the fourth plus log base 6 of y to the third. And this is dividing, so that's going to be minus log base 6 of z squared. Keep in mind, anything that's in the numerator will be a positive exponent, so it'll be a positive log, and anything that's in the denominator will be a negative log because you'll be divided by it. Negative log goes in the denominator. So therefore, this one was negative, but these two were positive. The only other thing we have to do is take each of the exponents and make them coefficients. So this is going to become 4 log base 6 of x plus 3 log base 6 of y minus 2 log base 6 of z. So I do it as a two-step process, first taking care of the multiplication and divisions, and then taking care of the exponents. And this is our expression in expanded version. I hope most people got that correct. Now, you could do this backwards also. If, let's say, gave you this expression, three log base 2 of x plus 1/2 log base 2 of y minus log base 2 of Z. What if I gave you the log in expanded version and I asked you to write it as a single expression, contracted back to a single log? In other words, I want this to be written just the log base 2 of something. I want something like this. I don't want this whole long expression. So I have to work backwards from the original way we did things. Originally, we first looked for the multiplication and divisions, and then we looked at the exponents. So if we're working backwards, we're first going to work with the exponents. I'm going to take each of the coefficients and make it an exponent, because that's where it originally came from. This 3 was really originally an exponent on the x, and this half was originally an exponent on the y. So any numbers in front of the word logs, just put those numbers back as exponents. Then go and see where you have pluses. I have a plus here, that means I'm multiplying. I'm multiplying x to the third times y to the 1/2. And this is minus, so that goes on the bottom, is just a plain z. Notice this is the single log base 2 of x cubed y to the 1/2 divided by z. Now, very often, especially if this is a multiple choice, this is a completely correct answer. But in a multiple choice, they usually will not leave a fractional exponent. So probably the better way to write this is log base 2 of x to the third. The y to the 1/2 means the square root of y over z. And that would be your expression contracted back to a single log. So we can take a complicated expression and expand it into its individual logs, or we can vice versa, take the expanded version and contract it back to its original expression. Okay, let me give you one to try on your own. Suppose I gave you this. A half log A. I'm using different letters now. Minus 3 log B minus 4 log C. Now you might say, hey, I forgot something. I didn't write a base here. But I want you to remember that something that we mentioned on Friday, that when the word log is written and there's no base written in, if there's no base written in, it's understood that the base is 10. It's what's called a common logarithm, and common logs work very well with our number system because our whole number system is based on 10. So if you have a choice as to what base to use, probably 10 is a really good number, because like 10 squared is 100. They're very easy numbers to work with. So therefore, in this case, if I didn't write the base, it wasn't that I forgot the base. I'm talking about a log base 10. Okay. let's see if you could contract that into a single log, into a single expression with just the word log once in front of it. I'll give you a couple of minutes to try that. Okay, let's work on this together. If you remember what I said, we're doing the opposite steps that we did before. We're going to take each of the coefficients and make them back into exponents. I'm going to write them. So that'll be, I'm going to rewrite this. Log A to the 1/2 minus log B to the 3rd minus log C to the 4th. In other words, each of the coefficients originally must have been an exponent. I'm making them back into the exponent. And now I can do the changing the adding and subtraction to division and multiplication and division. Now notice, this is going to be log A to the 1/2. That's positive. That's going to be in the numerator. But both the log B to these are both negative, so those both have to go into the denominator. So in the denominator, I'll have B 3rd, C 4th. Again, since both of these are being subtracted, it means they're both part of what we're dividing by. Again, when I see this A to the 1/2, I prefer writing it as the square root of A. So this is log square root of A of B 3rd C to, I keep doing it, B 3rd C to the 4th. And that would be your expression as a single contracted log. We're going to see how this is going to be useful next time. I'm going to talk about solving exponential equations and log equations, which is a major part of, and that's what we're going to talk about on Friday. I just want to do, we have a couple more minutes. I just want to mention a couple of things. I'm going to erase this. First of all, let's say I ask you this question. What is a log base 3 of 3 to the 17th power? Well, that's not really so hard to do, because if we call this x, and write it in, instead of logarithmic form, exponential form, we'll see that we'll get the base is 3. The exponent is the x, because that's the number on the other side, log equals exponent, equals 3 to the 17. Now, I think it should be obvious. What is the x equal to? Obviously, the x is equal to the 17, because 3 to what equals 3 to the 17? It has to be 17, which tells us a very important rule. If your number that you're taking the log of is an exponential form, it's written as a base to some number, and you're taking the log to that same base, if the two bases match, then your log has to be the exponent. If I ask you what's the log base 15 of 15 to the 0.2, the two bases match. The base of the log matches the base of the number that we're taking the log of. It doesn't matter what it is. And my answer has to be just the exponent of 0.2. That comes across very much so when we're doing log base 10. If I ask you, what's the log of 1,000? Which 1,000 could really be written as 10 to the 3rd. Remember, if no base is written in, we understood the base to be 10. So the log base 10 of 10 to the 3rd, now the two bases matches. Even more so, let's say I ask you, what's the log base b of b? All right, doesn't matter what the b is. Well, really, this means b to the 1, right? So obviously, this is 1. Anytime the base matches the number that you're taking the log of, then your log has to be equal to 1, because b to the 1 is b. So if I ask you, what's the log of 11 in base 11? Your answer obviously has to be 1. Just put it in exponential form. 11 to the 1 equals 11. When the two numbers, the base matches your number you're taking the log of, your log is simply 1 because your exponent is 1. Okay, what's the log of 10? Anybody? Log of 10. Anybody put it on the chat? Okay. Obviously, log of 10, there's no base written in here. It means the base is 10. It matches this, so the log of 10 has to be 1. And you could try this on your calculator. You push your LOG button, and you put in 10, and you press enter, and it'll give you 1. Okay, I just want to mention, so as we mentioned, common logs are on our calculator. There is another type of log. I don't know if you're required to know this, but I'm going to mention it. Something called ln. It's called the natural log. And if you, instead of writing the word log, you may see something like this, ln 15. Now, when you see this ln, and you'll see it on your calculator, it's either right above or right below or right next to the LOG button. There's an L, it might look like an IN, but it's not, it's LN. It's called the natural log, and it's a very interesting logarithm. The base of this number, of this logarithm, is a special number called E. E is called the natural number. So when you use a logarithm with that number E, it's called the natural logarithm. Now, why would this number E, and I haven't even, it's equal to 2.7, et cetera, et cetera, et cetera. To me, it's the most unnatural number. It's an non-repeating, non-ending decimal. It's an irrational number, sort of like the number pi, or the square root of 2, irrational, non-ending, non-repeating decimal. It pops up in certain situations in something called compound interest. In real life situations, this number pops up. I can't, if you take pre-calculus, it's one of the things you're going to be talking about. I'm just going to mention, so there's this number. So when I see ln 15, what I really am asking you to find is log base E of 15. Now, since you really don't know what the number E is, you can't really do this except with your calculator, because on your calculator, if you press the ln button and you put in 15, you'll get 2.708. That's what you get. You can just figure it out using your calculator. So that's why it's on your calculator. It comes up, again, it's called the natural log because it comes up in certain formulas that are very important in real life situations. But you could do something like this. What if I ask you, what's ln of e to the negative 3? Now that looks like it's complicated, except if you remember, ln means log base e, and this e to the negative 3. Well, we know that when the two bases match, the log is simply the exponent, so the answer would be negative 3. And if I ask you, what's the log? I'm sorry. I ask you, what is ln e? This is a very important thing to know. Ln e means log base e of e. Obviously, the bases match, the exponent is just 1. So ln e and log 10 are very important numbers. They're just equal to 1. Okay, I'm going to stop, unless somebody has a question, I'm going to stop here. I'm going to continue with, next time we're going to be reviewing chapter 6 and 7, which is radicals, et cetera, and quadratic equations and how to solve them. And we're going to be finishing chapter 8, which is the logarithm chapter. And what we have to do is learn how to solve logarithmic equations. We talked about solving exponential equations. We're going to talk about that again using a different method. Any questions? Okay, have a good day then. I will see you on Friday.